Welcome back to Retro Depot. Today we're going to be taking a look at the next evolution of the RD10 expansion device, or docking station if you will, for the MX-10 MSX computer made by Casio. Really kind of a neat project that we have going here. Essentially this is a clone of a device that wasn't available since the 80s, and by that I mean there's just not a ton of them out there. The ones that are out there, they're pretty expensive because there's not a lot of availability, and this is for a computer that's actually kind of on the budget end of the retro computers. It's not something that's got a ton of availability. So that said, yeah, we're just going to jump right into it. So the last time that we shot the video, we went over the testing of the device and exactly how it operates, some of the features that it has, and some of the design principles that I wanted to incorporate on my second version of the board. Now that we've verified that it's working, we need to figure out how can we improve it. Well, I touched on several things. I'm not going to touch on all of them today because they just really aren't pertinent to realistic consideration. We have to do them, but they're so simplistic it doesn't even matter. That being the power switch. We don't need to worry about going over that because it's simple to add a power switch into a design. We don't need to go into the power connector for the floppy drive because, again, that's pretty simplistic. It's going to be something that's relatively simple, and it's just connecting up a couple traces. Now, that's about where it ends. Reset is a different signal. That's got an entirely different problem. And the problem being is that I've actually taken a look at the torn down pictures of the motherboard provided by Daniel Padilla, and I've just determined that reset's out of the question. It looks like the reset is actually controlled by the CPLD, which means that we cannot bring that low without potentially burning out the CPLD pin or possibly some of the logic on that. So it's going to be an output signal only within both the memory slots as well as the expansion connector. So that's going to be output only. We are not going to be able to do a system reset by adding a button, which means that we are going to have to rely on that power switch in order to be able to cycle the machine. That should make the next version of the board simpler because now we don't have to unplug and plug back in the power supply. We can simply flip the switch off, flip the switch on, and the computer will reboot. So that solves that problem. But then it gets even more complicated. The next part that we discussed was actually integrating either an OPLL or maybe a floppy disk controller. And that's great in theory, but there was a problem. First off, I misspoke whenever I was talking about the slot organization in the last video. In my head, I was thinking the correct slot, which is the very beginning slot, because you have a total of 4, slot 0, slot 1, slot 2, and slot 3. But in the video, I actually said slot 1 instead of slot 0. The memory that we're concerned with is actually slot 0. And slot 0 is the slot that is internal to the machine. The single slot on the machine would be slot 1. And then on the adapter itself, you would have slot 2 and then slot 3. So we are concerned with addressing the very, very lowest slot in the system. And we know that this machine only has a 16 kilobytes of internal SRAM, or in this case DRAM. So we've got a 16K window there between 8000 hex and BFFF hex that we, in theory, should be able to potentially place a memory device in that location in order to be able to add expansion ROMs or additional memory, whatever it may be. So that's something that we'll take a look at. This video is going to be all about how do we expand this design. So the very last piece that we're going to look at is, actually we're going to look at it first because it is more simple, is we didn't mention something in the last video, or I didn't mention something in the last video that I should mention in this one, and that is that there's one other limitation of this particular board that I created. Now this particular board has a single voltage power supply input, and then it's regulated down to 5 volts. So we're taking 12 volt and we're regulating it down to 5 volt. But we have an additional voltage that we really need to create in order to have compatibility with all the cards out there on the market, and that is the negative 12 volt signal. The negative 12 volt signal, it's something that is required for a lot of music adapters, like sound card cartridges and things like that. But we could hook up just the negative voltage to ground, but that isn't going to give us the true range of the audio signal. So we need to do something about that. So that's going to be the first thing that we're going to take a look at. So one of the things that we need in order to make this expansion board more compatible with the MSX standard is we need to implement negative 12 volts. Now this creates a problem on this board, and the reason why that's a problem is because currently we only have a single voltage for the input supply, and it is positive 12 volts. And we do have a switching regulator here, but this switching regulator actually brings it down to 5 volts, and while we do have 12 volts on the socket here, we do not have a negative 12 volt signal. Now we do have some room over here that we would be able to put a circuit in order to create that negative voltage if we can figure out a way that we can do it. Well, luckily there is a pretty simple solution for doing things like this. We can use a IC called the MC34063A, and this is an 8-pin package IC. It's available in both DIP as well as SOIC packages, or surface mount if you will. And it actually requires very few components in order to run. It needs a resistor here for the load. It's usually a very low resistance resistor. Right here it actually specifies 0.24, but usually it's going to be somewhere less than half an ohm. We need a input filter capacitor, which on this board we actually don't need it because we've already got those here, but it does help to stabilize the input to the switching IC here. We need a couple more resistors here. These create a voltage divider for the comparator, and here it lists a 8.2 kilo ohm as well as a 953 ohm. We need a small capacitor for the essentially the charge pump circuit. This is what operates the oscillator, which switches all this stuff around. We need a inductor to ground, a Schottky diode, and we need a output capacitor. And then optionally we can put in a filter here. Now the purpose of this filter is actually to help smooth out some of the switching noise, and we are definitely going to want that because we are going to have this in a digital circuit. So we need to put in a 1 microhenry inductor as well as a output capacitor here in order to filter this out. Luckily we can use what's called a ferrite bead. And if you don't know what a ferrite bead is, it's pretty straightforward. They are really simple. They look just like this. We'll zoom in a little bit for you here so that you can see these things. But yeah, it's just a ferrite core, usually with a single lead that goes through it, and it's bonded in here so that the lead doesn't shift around, or the little ferrite core doesn't. But usually these comes in values of 1 to 1.5 microhenry. I believe these here that I have are 1 microhenry. Maybe they're 1.5, but in whatever the case is, they'll actually work just fine. So we'll need one of those, and like I said before, we'll need that output capacitor here. Now there's a couple of these that you need. This one here is a 1000 microfarad, and this one is a 100 microfarad. You know, with that, you've got a little bit of play in this. To be honest with you, this IC is very, very friendly. Zoom that camera back out so that you can see. But yeah, no, we've got these two right here creating essentially about 1100 microfarads on the output, small inductor there, and it doesn't really take much to get this thing operating. Now, I've actually done some work ahead of time, and I came up with this board here. Now, we'll zoom in just a little bit here so that you can see this, and it's pretty simple. We have our 34063 alpha IC here. Now, instead of a input resistor or load resistor, if you will, I've actually got some wire here, and this is actually what's called nichrome wire. You can buy it in short little reels like this, but it produces a known resistance for a given length. And by winding this up into a thicker wire, I'm able to accurately measure out how much resistance I need by length, and then I can actually solder that into the circuit and create a resistor. So that's what this little piece of wire is. That's actually acting as the resistor itself. This is the same type of stuff that they use for wire wound resistors. And if you don't know what those are, it's just a different type of resistor. It's used in various different applications, but mostly for a load resistor. Now, having said that, we've also got a couple other things here. Obviously, we've got our voltage divider here being created by these two resistors. We've got our Schottky diode. We've got our output ferrite or inductor rather. We've got our little capacitor here that's in charge of the switching circuit. Now, this is a, I believe it's a 3,000 picofarad capacitor, so it's a little bit higher rate, which means that it's going to actually oscillate at a lower frequency. We've got our two output caps here, and then if you look up underneath here, I also have my ferrite bead, which is being used for that 1 microhenry filter. And then I've just got a couple leads here for inputting the voltage. One of them is marked with stripes so that I know that's the negative voltage. And then I've also got a little place to clip some leads on here so that I can test these voltages. So, having said that, we need to actually test this to make sure it works. And obviously I've already done this, otherwise I wouldn't be showing it on camera. But we do want to set this up so that we can accurately measure exactly how much we're going to be able to get here. So in order to do this, I've got a really cheap multimeter here. I'm actually going to turn on a power supply. Now, this power supply is already set up to be outputting 5 volts, and we are going to test that real fast just to show you that there's no magic going on here. So if I clip up my negative lead and I clip up my positive lead, actually let's turn our meter on first. You can see that we're reading just ambient noise there. But if I put this in, we're reading exactly 5.02 volts. So what we're going to do is simply hook this up, and now the circuit is operational. Now, we could hook this up just like this, but the reality is that we actually have some of these terminals here. So we're going to clip on right here, and we are going to clip on right here. And as you can see, we're now getting, what is it, 13.68 volts in the negative range. So negative 13.6768, somewhere in that area. So it's a bit over 12 volt, but if you've ever taken a look, especially at a PC power supply, the 12 volt rail will very often run closer to 14 volt than it will 12 volt. And whenever I've measured this with the oscilloscope, I'm actually reading about maybe 1 volt peak to peak, because you do have a certain level of oscillation because of that charge pump. And you can filter that out further if you like, but I think for the application that we got here, I'm not going to have any problems with it whatsoever. As a matter of fact, this thing doesn't even get hot, and you can actually put in a pretty good load. To give you an idea on how much of a load you can actually put into it, you know, I mean, I can grab, let's say, a 500, and actually let's go with about a 470 ohm resistor here. So if I grab a 470 ohm resistor, just so that you can see, that is, I'm not sure if you can see that or not, but that is a 470 ohm resistor. We can actually take this and plug this right in, and it will get hot. You know, you can definitely feel it heating up, but the voltage is staying pretty consistent, and yeah, it's capable of outputting a pretty good amount of current. Like I said, I mean, that's not a ton, but obviously it's going to be, you know, 10, 20 milli ohms, somewhere in that range. So it's stable, and that's what we really want here, because mostly this is going to be used for, again, a voltage reference for any type of audio amplification circuit that you may have in a cartridge. And like I said, these cartridges, for example, this is the SD512. There's some of these that actually have audio outputs on either side. Matter of fact, some of the cartridges have gains with the audio circuitry actually on the cartridge itself for like complex sound effects and things of that nature. So this is going to work out very nicely. And like I said before, it's going to be small enough that you could actually fit something like this into this space. So that's what we're going to plan on using for the negative voltage circuit. And I think it's going to actually work out very well. Like I said before, this thing doesn't even get hot, and if you actually hook this up, the oscillations are all inside of the chip itself, so there's very little going on outside. Really, you may have a little bit of a ripple on the output, but for the most part, even though my scope said that it was getting about a 1 volt peak to peak, the reality is that I wasn't able to really see that in my measurements. Obviously the scope is telling me it's there, so I have to believe it is there, but it even read that 1 volt peak to peak range at 0 hertz. So it must be a really slow rise and fall over time. So I think that's probably what we're looking at, and probably a lot of that is due to the charge pump. So even if that is the case, I think that we're going to be very well served by this small little circuit. It's cheap. You can get these ICs for usually in the range of about maybe 75 cents to $1 through DigiKey or Mauser. You've got a couple other components here that are obviously going to add in about $1 worth of extra cost, but it's not going to be a whole lot. This negative 12 volts is going to cost you probably $2 overall, and you're actually going to have a lot more capability with using that rather than just trying to use a ground reference. So that's what we're planning on using for the 12 volt circuit. Now that we've taken a look at the 12 volt, or the negative 12 volt signal that is, we need to take a look at the way that we're going to be able to add in the memory as well as additional devices onto the board. Now I'm going to be flipping back and forth between computers on this in order to present this data to you, but suffice it to say, I think I've come up with a pretty good solution here, so let's take a look at it. Okay, so in order to be able to tell whether or not the memory in the MX-10 is actually mapped to both of the 16K windows in upper memory, we need to do some testing within the computer. And one easy way of actually achieving this is to write a small basic program. Now this basic program, it's only a couple lines of code, and it tells us all the information that we need in real time. So what we'll need to do is obviously clear the screen so that we start off with a fresh little notepad here, if you will. We're going to load the decimal value of 8000 hex into memory, 8000 hex. And we're also going to load up a variable with the memory location and decimal for C000 hex. And then what we want to do is we want to create a for loop. So we're going to have this thing go for a 16K memory space. And what we're going to do in this for loop is we're actually going to print the value contained within A as well as the value contained within B, increment both of those values, go to a subroutine and return just as a small little delay. And then we're going to go on to the next for loop iteration up until the point that we reach 16,384, at which time it's actually going to jump down to 300, which is just a rim statement, just to have a placeholder there, and then it's going to end the program. So if we run this, and I'll do that right now, we can begin printing numbers, and if we stop our program real fast, we can take a look. This first column here is going to be address locations 8000 and on up. Over here on the right, it's going to be location C000 and up. So it's printing out the corresponding memory location exactly 16K in memory apart. And as you can see, we're getting FF in all these locations. 255 would be the way of putting FF in decimal, FF hex and decimal, that is. And of course we can see in these memory locations we do actually have data in there. At least it's showing us that in the decimal form. So if we go ahead and run this program, you can see it clock on along, and you can see this is pretty consistent. We're getting the same differentials here, and of course now we're starting to get random data. So if we pause this and take a look, this is actually the startup memory, essentially how the memory initialized. And it's not uncommon for it to do this. Sometimes it'll be, FF, sometimes it'll be AA. It kind of depends upon the memory in my experience, but for the most part, just about every type of SRAM or DRAM is going to start up with this garbage in it. And that's pretty consistent for what we would expect. Now, if you notice over here, we've got a solid amount of numbers here. Instead of being alternating like this, like you would normally see, we're actually getting the same values over and over and over again. And that's a pretty good indicator that there is nothing addressed at this location. So therefore, whenever we are designing what add-ons we want to put inside of the computer, or in the expansion that is, we know what memory locations are open. So we can actually decode for slot 0 in the 8000 hex to BFFF hex series of memory. So essentially that third window of 16 kilobytes within the Z80 address space. We're going to be able to decode for that and be able to use that memory space to add in either ROMs or RAM, whatever we really want to put in there. We need to take a look at slots and see exactly how slots work in order to understand how we're actually going to make this work, assuming that we can actually address that 16 kilobyte area of memory. So I've got the MSX technical data book. This can be found online. This one's presented by Rob C's MSX Workshop. Shows who originally scanned it, who converted it to PDF, so on and so forth. But I've already bookmarked a couple sections here. So the first one is on slot decoding. And if we have a look at this, we can get quite a bit of information here. So internal to the MSX architecture, they have what's called the PPI, which in the original it was 8255 PIO, which we're all familiar with that if we've looked at my G80 computer, because this is what I use for user I/O on the board itself. But long story short, on port A, it writes values to that, which is then taken into a demultiplexer, and then it spits out two variables, A and B. So the way this works is that this is your 88 register. That's A as in alpha, 8 as in the number 8, and that's hexadecimal. But it's within your I/O space. And long story short, each one of these 2 bits here, so CS0, CS1, CS2, and CS3, those are a 2-bit binary number, which allows you to select up to 4 devices. And that represents, obviously we have 4 sets, so that represents the 4 16K memory windows within the Z80 address space. And then we are using those to come up with a 2-bit output based upon the inputs A15 and A14, which would decode for those 16K memory spaces. So when these are at a given value, it's going to select 1 out of 4 of those 16K pages. It's then going to propagate the inputs from this onto the outputs, which allows you to read, okay, in this 16K memory space, what bits are set. And then it uses those through a 74LS139 2 to 4 demultiplexer. And that allows you to figure out whether it's slot 1, slot 2, slot 3, or slot 4. And of course, these have to be gated with both memory request as far as refresh in order to be a valid slot select signal. Now, also down here of note is the reset signature. So anytime that a reset takes place, it's going to basically take this SR latch and it's going to flip it. Now, if I'm not mistaken, this actually should be NANS here, but yeah, I believe I used NANS in my schematic, but essentially you just have to make a SR latch, and you know, that will reset this whole thing, clear everything out. But long story short, yeah, this is how you decode for the actual slot signals themselves. Now,
what if we wanted to create more than one I/O device? Because we know we have 16K of memory space that's available. Now, of course, we still have to figure out whether or not we can actually decode for it and get any conflicts. We won't be able to tell that until we actually build the system, because with the MX-10, it has a CPLD, which is so cryptic in what the pinout is, we really don't know. So we're going to actually have to build it to test it. It could be a complete fail. But that's okay, because this is going to teach us a lot about how this computer architecture works. But let's say that we had that 16K address space, and let's say that, for example, a floppy disk, the ROM for that's going to be typically about 16K in size. So what's to prevent us from, putting more than, one device in there along with the information to be able to use it? Well, in short, we've only got 16 windows, right? We've only got 4 slots. Well, that's actually incorrect, because each one of these 4 slots can be further divided down into 4 additional slots. Now, these are called primary slots, and whenever we divide it down even further, it's called subslots. And if you look at this page in the MSX hardware manual or technical reference, whatever you want to call it, it's actually got some example circuits of exactly how this works. Now, in short, we have to have an additional register. Now, this register, instead of being in the I/O space, is actually in the memory register. And we can see it outlined here, but it's the memory space FFFF within the primary slot. So within that primary slot, if we write to this register, we're going to be able to save that information so that we can use it as a way of decoding an additional 4 slots, and within each one of those slots still have that 16K memory page, 4 times over, that is. So it basically, the data bus comes in, they latch it into a 74LS73. Now this can be read back as a complementary of that amount in order for error checking and things of that nature, and that helps the computer determine whether or not mostly whether or not it's actually a valid, page register for a expanded slot. And then, of course, we have our latching clock here. This is essentially a chip select signal that's access to FFFF, write, as well as slot select, which would be slot select 0. It then takes those 8 bits and it puts it through a 74LS153, which, if you want to go back up here and take a look at this, it's the same circuit that we're using here. And then it's further putting those things through another 74LS139, which is again the same thing that we did with the previous one. And then with each one of those select signals, it decodes it and it gets the proper address space. And of course, there's protocols for how to determine flow of bus control and things like that. That's where it starts to get a little bit more complicated. But let's say that we just wanted a 16K window in memory. How would we do that? Well, we're going to open up digital, because in digital I actually have this set up here, and this is a fairly simple circuit, and this is not going to be exactly how I design it, but it shows you exactly how simple that is. So here we've got a couple things. We've got that slot A signal and that slot B signal. Now we know that in order to get to slot 0, which is what we need in order to put it into that open 16 kilobyte memory space within the computer itself, both of these signals have to be low in order to get what would be called slot select 1 or slot select 0. But we also have to combine that with memory request as well as refresh. And we want the refresh to be high and the memory request to be low. So we can knot the refresh and then put both of those through an OR gate, put the 2 slot select signals through NOT gates in order to bring them up high, which will then use a NAND gate in order to bring it down low. And then if either one of these 2 signals are low, or if either one of them are high, this slot select 0 signal here is going to be invalid. But if they're both low, then at that point it's going to be active, which means that your 74LS138 here is going to be active. Now, well, at least a portion of it, because we're feeding it into one of the active low chip select signals here, because it's got 3, 2 active low and then 1 active high. The active high, we can just tie that to VCC. C, which is the third bit in the decode address space of this device, we're just going to tie it to ground to keep it low so that we can use the lower 4 bits of the decoded memory space here. And because this is the third bit in the register, we need bits, the third 16K page of memory. We need the third set of bits in the register, so that's going to be bits 4 and 5. So once we have those, we can latch those into that memory space, as you can see here with the FFFF chip select signal. So that's going to be an active low signal within that address space, and it's going to latch the outputs. And then once it does that, whenever the computer is reading from 8000 hex to BFFF and it's slot 0, then the outputs are going to be active for whether it's in the primary slot, which is slot 00, the subslot slot 01, the subslot 02, and the subslot 03. So by doing this, in theory, we can actually address 4 different ROMs within that address space. But there's another catch, is we're not going to have any memory space left over. And that's important because many of these devices actually use the memory space in order to work. And I'll go over that here in just a minute, but long story short, we are going to be able to access, like I mentioned before, a total of 4 16K windows within this 8000 hex memory space. So if we take a look at this, we can actually bring this high, we can bring that low, and of course we've got a solid output here, so just one of these signals going high is going to be enough to turn this thing off. So we want to make sure that we keep it in this manner. We're going to go ahead and keep that high so that we can just use it as a toggle bit. Now as we can see, both of these bits are low, so if they're low, we can latch that data in, and then whenever it reads from that location, obviously that first bit here, slot select 00, is going to be active. But what if we decided that we wanted to put 01 in that space? By latching that data in, now whenever we have that chip select, we get a different bit. We get bit 0, and that's actually backwards. Yeah. So these 2 signals should be switched. Let's do that real fast. So we're just going to grab this and switch these up. Okay, so now if we go back and we set this bit, the first one, now we've written that first bit. Whenever we use our chip select here and of course set refresh, now that second bit is set. Now if we flip these bits and write them, chip select the third, and if we do both of them, write the data, chip select now the fourth. So we're able to access, like I said, that 16K page of memory within every slot. And of course, like I said before, we don't need to worry about the address buffer, or the data bus buffer on this, because we are using resistors at the moment in order to simplify this design. But long story short, we should have no problems with addressing this. The only consideration we are going to have is if there is something that's causing the FF signal on the data bus whenever we read that memory space, as we saw on the MSX. If we have something along those lines, this is going to be moot. We'll be able to build it, but we're just going to get a machine that locks up whenever we try to access that. But the other consideration is going to be the other bits within this subslot, or this subslot register here. I'm not certain if we actually need those bits, and if we do have those bits, if the computer will try to access that information. That's yet to be seen. So we will have to take a look at that, and that's going to be, unfortunately, something we will have to test through trial and error. Now, the next thing that we need to discuss is the I/O ports that are contained within the computer, and the reason for that is that with most of the devices that you're going to find on, let's say, ROM cartridges, they are designed to utilize memory. They're memory mapped I/O. And that's problematic for a couple reasons, but in this particular situation, it's problematic because the MSX standard has defined I/O ports for certain types of items. So that said, I've actually found a really nice page that I've been using, and I'm going to post a link in the video. But what this website has is a listing of all those I/O ports, and it's got all kinds of information on different machines, the I/O ports, exactly how they're used. You name it, the information is probably going to be here in at least the most basic form. But it's very handy to have, especially when we're looking for ports that we can use. Now, the first thing that we need to take a look at is obviously the floppy controller, because that's one of the big things that we want to add here. And if we go down and we take a look, you can see that there's actually a floppy drive controller that is used on ports D0 through D7. And we can replace that with our own controller that's based on the WD37C65. Which is the same one that's used in the TDC 600 floppy disk card. So we've got a location here that we can stick that so that it's not going to interfere with any of the typical expansion cards that we find. So this is going to be a good option for us. And as far as the OPLL, which is something I've considered adding as well, there's actually a port for that as well. And that's actually right here. It's 7C through 7D. It's reserved for the MSX Music slash FM Pack slash OPLL. So that's another good option there. However, we've got another problem, and that other problem actually has to do with the programs. And so let's take a look at the TD600 ROM. Now, I've offset this, and the problem with the ROM is that it actually begins in the memory area of 4000 hex. That's where it's designed to boot. And unfortunately, the source code, if it is still out there anywhere, is not available to the public. So we don't really have a way of handling this very easily. So we've got to do something about that. And what we do about that is we actually have to disassemble it. So I've actually got the 8080 disassembler here. I've got it set up for Zilog mnemonics. And we need to go ahead and add in our offset here. And once we've done that, we can disassemble this. And it's going to take a few minutes to generate the listing of the code, as well as all the jump locations and things of that nature. But it's going to eventually do it to the point that we can start comparing this byte by byte. Now, if you take a look at the source code itself, this goes all the way down to essentially 8000 hex. So it's only got, probably, 100 bytes or so of free space within this ROM. Everything else is actually occupied. So it's going to be quite a chore, because we've got to do several things to this in order to make it usable within that memory location that we're going to have available to us. Now, once this is done, listing this program out, we're going to be able to actually go down here and take a look at this byte by byte. And it looks like this actually didn't compile it the way it should have. Oh, well, maybe. Let's take a look. Let's scroll down. Okay, so now for some reason it's still, I put in the offset, but I think you actually have to load it up. But it will still disassemble. But the point being is that you're going to have, what did this do? Okay, so there it is. It did end up disassembling it down at 400. It just added the extra bytes. Okay, well, that's a little bit inconvenient for what we're doing here, but it's good enough. So as you can see, we've got load BC, load BD, load LA, load DA, halt instruction, and then load H with L. What that is that is actually this first little piece of code. That's the identifier and I think the manufacturer number and a couple other things. And then after that, we start seeing our actual code. So we've got jump locations here, which is consistent because C3 would be a jump, C3 is a jump, C3 is a jump, C3 is a jump. So we've got lots of jumps here, and that is exactly what we're seeing in the code. However, the things that we are going to have to modify is actually going to be the text. So if we come down here and take a look at some of the text in this, let me see if I can find something here. Oh. Okay, so we've got Disk Basic version 1.0. Now that's fantastic. Let's go down to 5BE0. Matter of fact, let's go this way. See if I can get it here real fast. Well, that's 5C. Okay, so it's going to be somewhere right in here is where we're seeing this at. So should see an ODOA, and I'm not sure exactly what those bytecodes are, but it's going to be somewhere right in here. So anyways, all this right here is going to be text, and it's actually going to be this text for the Disk Basic version 1.0, and then it's got a couple of terminators right here. But this is actually showing up, if you've never done this before, it can be a little bit confusing, but it's showing up as the actual opcodes because that's what it thinks this is. Now there are some tools for being able to define data areas, and we can go in here and we can add this information in, and we can have it know that, hey, this location here is actually a piece of text, or it's a data string or something like that it needs, but we don't really need that at the moment. Everything else about this is going to compile perfectly fine, I think. But obviously we will need to change this, and we'll need to make sure that all the jump locations are actually jumping to identifiers. For example, let's see if we can find one here real fast. So here's a call. Notice I was calling an identifier at 5EAD. And here's a location that it's loading from memory. It's got several different things. We need to make sure that all these locations right here that it's at least dealing with within the ROM are actually going somewhere in the new address space. And of course, the way that you do that is with these identifiers here. So we're going to have to go through and actually hand patch this ROM. And with it being 16K, that's a lot of work. It's exactly what I did with the tiny basic ROM for the Z80. I actually pieced that. Well, at first disassembled it from a working binary, and then I used the source code to go back and verify everything was correct, because the scan for the original source code, some of it is not exactly the most legible, and it's easier to disassemble it instead of typing the entire thing in. But that was only 2K of code, so we've got 16K here, which that's a lot of code. That's actually a larger ROM than my G80 computer actually uses altogether, along with Tiny Basic. So it's going to be a lot of work, but it's something that we absolutely must do in order to be able to use this ROM. Otherwise we're going to have to write something from scratch, and that's not really something I intend to do. I don't really intend to rewrite a ROM for MSX1 on this computer. It's just beyond my technical knowledge of the MSX DOS system, and there's no point in doing that whenever we can actually just work backwards from somebody else's product that's already working. So we should be able to patch this and get it working. It may take a few tries, and it may take some some brainstorming to figure out what's going on, why it's not operating correctly, but it's not too difficult to patch this into a new memory space. We just have to take the time to do it and put in the effort to make sure it's done right. And of course, the same thing would have to be done with the OPLL. Once we, switch over to the OPLL, it's got, the MSX Music ROM, and we're going to have to change that, I think, as well. Although, if I'm not mistaken, because I'd have to take a look at it, I think that on Sergey Kislov's Omega computer, I think that I actually patched that ROM in, and if I'm not mistaken, I think this one's somewhat portable. I think that you can put it in a couple different memory locations. So that one may be as simple as just plugging and play. It's hard to say. I'll have to, do a little bit more research in it. But yeah, that's essentially what we're looking at here. Most of this stuff, I think that we should be able to make some changes. Of course, this does address the floppy disk controller at, I believe it's memory locations 8,000 and 9,000, if I'm not mistaken. I'd have to go back and actually read the theory of operation on it that was done by a guy on the Retro Brew Computers forum. But we're going to have to actually go in and find those routines and change that so that it's actually writing to the I/O space, and that may even affect some of the ROM itself and how this stuff operates. So we're just going to have to see how that works. It's kind of hard to say, but in theory, considering all this stuff has named locations here instead of actual memory locations, it should be a little bit easier to do that.
I'd like to thank you for taking a look at the video today. Like I said, this is a project that probably not a lot of people are going to be interested in as far as actually building one of these. Certainly there's going to be some people out there with MX-10s that wouldn't mind having an adapter like this. But for the most part, this is probably a video that's more interesting as far as the design process goes, figuring out how you can add in additionally peripherals to a given computer system, and essentially just kind of the design stages involved therein and considerations that you have to take in order to be able to create a device such as this. So again, I'd like to thank you for taking the time to come out and watch the video. Check out the website, retrodepot.net. These boards are not going to be offered on the website. However, if you're interested in obtaining one, even one of the early ones that clearly works, you're welcome to contact me. I've got a couple of those I'm going to be willing to give out to people because I've already built the one that I need. I've got, I think, 4 or 5 extra boards over there, so I'd be more than happy to pass some of those out. Just pay for the shipping on it and you're good. And I'll provide you with a bill of materials that you need in order to build it. I'm not going to provide you with the actual chips, but I'll provide you with the list that you can order. But yeah, welcome to contact me about that. If you have any of your personal projects that you'd like me to take a look at, always willing to do so. We want to take a look at those, kind of give my opinion on it. I'll even shoot a video if you'd like. And then obviously, check out the website, like I mentioned before. We are on Twitter now, so if you'd like to check us out on Twitter, I'll put a link down below. I'm going to also put a link down below for the material that I used for this video, as far as the links to the technical reference manual for the MSX standard, as well as the page that lists the actual I/O ports. That's going to be pretty important if you're doing something similar on a different project. But check in next time. We'll hopefully go over some of the things that I've implemented since then. But until then, thanks for coming out. Hit like if you liked it. Hit dislike if you didn't, because I do support that. It tells me what you like and what you don't. If you want to see more of my videos, or if you thought this was an interesting project and you just want to keep up, feel free to hit the subscribe button. I'm always, willing to take subscribers. I think we're up to about 1,500 on the channel now. I think that actually rolled over a couple days ago. I think we're probably 1,502 or 1,503 now. So yeah, fantastic. It's great. I never would have thought that 1,500 people liked my videos. So here's to that. But again, thanks for coming out. See you next time.